In the next few videos, we're going to do a deep dive into linear approximation and differentials. But in this video, I want to do a brief introduction to what linear approximation is and how it can help us. So here we have the graph of some random function y equals f of x in red. And in blue, we have the graph of a tangent line to that function. And by now we all know that the slope of that tangent line represents the instantaneous rate of change of that function at that particular point. But here's what I want to do. I want us to really zoom in on that point of tangency. Zooming in just a little bit helps us to see that the curve itself, the red curve, appears to have flattened out around that tangent point. Let's zoom in a little bit more. This is the same curve, the same point of tangency, and the same tangent line. What do we notice here? Zooming in even more, the curve at the point of tangency appears to flatten out even more. And by now it's easy to tell that the red curve appears to be getting closer and closer to the actual tangent line. Let's zoom in again. Now we've really zoomed in on that point of tangency. And as you can see, the graph of the tangent line and the graph itself are almost indistinguishable. That's how close together they are. That's how close the blue tangent line approximates the actual graph at the point of tangency. What we've just shown is an example of local linearity. As we enlarge a curve near a point of tangency, the curve appears to straighten out and approach the tangent line at that point. And this observation leads us to the idea of linear approximation. Linear approximations give us a good way to simplify more complex functions into linear situations at any given point. For instance, linear approximations can be helpful when we are evaluating square roots of numbers that aren't perfect squares. Okay, so what does this mean? Let's assume this red function is an extremely complicated function. It's hard for us to find derivatives of and work with, but we're really interested in what's going on at this curve right around in this area. So surrounding the point of tangency. To make things simpler for us, we don't even have to use the curve itself. We can just use the tangent line, because the tangent line is going to be such a precise estimation of what is actually going on the curve itself that it's almost indistinguishable from the curve itself. To come up with a linear approximation at a point, obviously we're going to need to be able to find the equation of the tangent line to the function at that point. This is nothing new for us. We've been finding equations of tangent lines nearly all semester long. To find the equation of the tangent line, we know that we start with the point-slope form of an equation. Y minus y sub 1 equals m times x minus x sub 1, where x sub 1 comma y sub 1 is any point on that line, which will be our point of tangency, and where m is the slope of the tangent line at that point. And again, to make this work, all we need is an x-coordinate, a y-coordinate, and a slope. So we plug in our x-coordinate of our point of tangency, our y-coordinate for our point of tangency, and our slope at the point of tangency, and solve for y, and that gives us the equation of a line, and we're going to call that line L of x. And we know by our previous demonstration that L of x, that line, is going to be a very good approximation of the original function at that point of tangency. So then for very good approximations, we can just use the linear model instead of the more complicated model for the actual function itself. In the next video, we'll do a quick example of how we can use linear approximation to find the square roots of numbers that aren't perfect squares.